All right. So on Friday, we left off talking about diastereomers, and we added that to our definition of enantiomers. And so when I posted the notes, I kind of added a little bit more to it. Oh, let me do this right quick. Um, I kind of added a little bit more um, to that definition. And so we talked about diastereomers being stereoisomers, but they're not enantiomers of the original image. They are not mirror images of the original. And in order for you to have diastereomers, you got to have at least two stereo centers. So we talked about that. Um, and in the notes that I posted, I gave another example. You can see here, right? If we had A with those two stereo centers, and then I have those two isomers, those two would be enantiomers. And so the diastereomers of A would be shown here, right? Where you can see if you compare this diastereomer right here to A, then you'll see that this stereo center right here is different, right? But the other one stayed the same. It's the same thing for the second diastereomer that I have shown at the bottom, where this stereo center stayed the same, and then this one changed, right? So that gives you an idea about diastereomers and what what you have to do to uh, depict a diastereomer. Basically, you're just changing one stereo center at a time instead of changing them both. Because if you look at the enantiomer, you can see immediately that both the OH and the bromine have a different configuration, right? All right, so with that being said, let's jump back up here because I think we got enough information now between the configuration and drawing the different stereoisomers. I think we got enough information to work on a few of these problems. All right, so let me ask you a question here. So we're gonna do problem. Is that I? Yeah, that's problem I. All right. The question is, well, let's just work this. So let me cut it out because we're gonna work through this and work all of our concepts at the same time. Let's see if I can cut it or copy it, put it on a new page. Just give me 1 second. And then we're gonna do some. Today we're gonna also touch those Fisher projections and talk about those. Those are not that bad. So we're gonna knock that out too. All right. So here's our example. Let's try to try it out. There we go. All right. So here's the question. It's gonna be a multi-part question. All right. First question is, how many stereoisomers are possible? That's the first question. Question. How do we
God
calculate?
damn.
Really? How do we calculate that?
It would be 2 to the n of how many stereoisomers you have. I mean, chiral centers.
Okay. How many chiral centers do we have?
8.
All
I'm sorry, 7.
right. We got chiral centers here, 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 and here. You said that's 7, huh? What is that? 2 squared, 16. How many is that? 16 times 8. 100. Is it 108?
128.
128. Yep. So you got 128 possible stereoisomers. All right. Here's the second question. Same example. What's the configuration? Actually, let's just go through and do them. All right, what's the configuration of each stereo center? Where you want to start? You want to start on the right end or the left end?
The right.
All right, we're going to start right here. So this stereo center right here, is that right?
Yes.
Okay, so of those two, so let's find the substituents. So I got an OH here, I got a carbon here, I got a carbon here, all right? And
A hydrogen.
hydrogen, that's not shown, that's right. Going back into the page. Okay, so where's one? Which one of the priority wise, which group is going to be one?
It would be
The O.
Oxygen, right? Which carbon is going to be 2?
the one closest to H, I think.
The one on the left.
The one on the left because it's connected to a method.
Yeah.
So this is going to be 2, and that's 3. Is that right?
Yes.
Yes.
Wait, Dr. Russell, why is 2 again?
Because remember we talked about the branches the other day?
Yes.
Yeah. So that methyl group right there
Okay,
is like a branch compared to 3.
Okay.
All right. So is that RS?
S.
It's counterclockwise.
Counterclockwise, isn't it?
Yeah.
We'll say that that's
Oh.
following. Is that right?
Yes.
Yes.
So the first one is S. Let's do the second one. I'm gonna change the color of the pen. So this second carbon right here, that's the one we're looking at. So what's the fourth substituent there? There's a hydrogen. Which way is it facing?
I'm sorry, which one are we looking at?
Right here in pink, the one circled in pink. We're just going down the line.
Would it be to the left of ME?
Yeah, it's going, but is it going into the page or out of the page?
Out.
Out of the page.
The methyl is wedged coming out, right? So the hydrogen will have to be going back. The direction left or right doesn't matter, but it's on a dash. All right. So which one of those 3 carbons, because we're looking at these 3 carbons right here, the CH3, this carbon, and this carbon. Those are the 3 groups that are attached to that chiral center. Which one of those is going to be 1, do you think?
I want to say the one close that's connected to the chlorine.
Yes, you're right. Right, because this is carbon, this is carbon, and this is carbon. So the rule is to go to the next substituent if both atoms have the same atomic mass, right? So on this carbon right here, if you look at what's attached to it, it's attached to chlorine. On this side, it's attached to oxygen. The oxygen is lower. I think oxygen is 16 and chlorine is 35. So that carbon on the left is going to be top priority. And then the other carbon, where the OH is going to be 2. And then that makes the methyl group 3. Anybody not see that? All right. So is that clockwise or counterclockwise? And again, we're looking at this carbon right here. Is
Clockwise.
It's clockwise.
Clockwise.
And then H is on the dash already. So we're going to say that this one is R. Are y'all following?
Yes, sir.
Yes.
Let's go to the next one. Now see here, we're going to have this one is going to be a little tricky because the two carbons are identical, right? Because now we're looking at this one. Right here, this carbon. So we know chlorine is going to be 1. Is that right?
Yes.
Because my other two groups are carbon and carbon. Now, how do I distinguish between them? What am I looking for? What do I need to do? If I'm trying to, excuse me, if I'm trying to prioritize those two carbons, what do I need to do?
Don't you have to go to the next
Look
atom?
for more.
To the next atom. And in this case, the next atom is
Chlorine, oxygen.
right here. Is that right? That carbon and that carbon. So those are the ones we got to compare. And then if you look at what's attached to them, one of them is attached to chlorine, the other is attached to oxygen. You following?
Yes.
Okay, so which one is going to be higher in priority? Which side?
The left side.
Left side. Good. So this is going to be 2, and then by default, that's 3. Is that right?
Yes.
R or S? Is it clockwise or counterclockwise?
It's an S.
Counterclockwise.
Counter. Okay, good. So this is also S. Is that right?
Yes.
All right, let's do the next one. So we got 3 down and a boatload to go. All right, let's do, this is a good one. Let's do this one right here. We're just moving down the line. But that's not highlighted very well. Come on, man, pick a color. All right, we're gonna do that one that's that I have in brown. All right. So can you tell me what 3 is automatically?
Probably the same as the last one.
So 3 is gonna be this methyl group right here. Right, because do you know that these two carbons over here are both bound to other stuff, right?
Yes.
Right, so that one of those two is going to be 1 and the other one is going to be 2. Which one do you think is going to be 1?
The one with the double bond.
Bonded.
Where's the double bond? All the way on the end?
Yes.
We don't have to go that far. Remember? Look right here.
Oh, the OH. Oh, because it's
that.
dashed.
Wait a minute. Look at that. And then look here. Following?
You lost me.
Which one of those two is going to be higher in priority? The branch one?
Wouldn't it be the one on the right?
The one that's branched. Is that right? So we got, this is 3. And then the carbon on the right, which is the one we just did right here, right there. That's going to be 1. Everybody agree with that?
Russell,
Go
can
ahead.
you do a different color for the priority numbers? Because
Oh,
all
you
the
want?
brown is just blending in together.
Oh, Lord have mercy, Jesus. All right, I got you. Let me switch pens. That's the beauty of this being digital. I got a million colors over here. Let me see if, let me not do that. I'll just do red. What about that? So this is 1. You agree? Is that better?
Yes, I thank you.
All right. And this is 3. And then that makes this carbon over here what? 2. Do you see why we had to go to the next atom? Because right here and right here, both of those are bonded to chlorine. Right. So we have to keep going until we get to a point of difference. Does that make sense?
Yes.
So what is that stereocenter? Oh, let me change the brown in there too. What is that stereocenter right here? Is it R or is it S?
It's
S.
it's counterclockwise.
Counterclockwise. So it's S. That's right. So let me erase all of this priority stuff and all this brown and put that in there. So that's S. All right. We okay so far?
Yes.
All right. Can somebody do the next one? Sorry, I'm gonna turn this phone down. Can somebody do the next one? Anybody? For a bag of Doritos?
You mean the one
Hey.
attached to the chlorine?
Right there.
Okay, I can try.
Come on with it. You can do it.
Okay. So the first group would be the one with the chlorine attached.
Good. Okay, I agree with that. So chlorine is first priority. I agree with that. If I could write
And then wouldn't the second group be the one with the methyl?
here.
Yes.
Mm-hmm.
And then the third group, would that be the little carbon down there?
The CH2. Yes.
Oh, okay.
Yep.
And then
So go ahead.
since it's clockwise, then it's gonna be R.
Good. Very good. I agree with that. Anybody disagree? All right. Let's do the next one. Somebody do the next one. I think we got enough under our belt now that we can do this with no problem. Somebody do the next one. That's a dashed line, by the way. It's just the resolution is just bad. So the wedge is going to be a hydrogen coming up. All right. So who's going to volunteer for that one?
I guess I could try.
Do you ever seen Star Wars?
A little bit.
A little bit. You know who Yoda is, right? Y'all know Baby Yoda from the Mandalorian, I'm sure. But Yoda on Star Wars says there's no trying, there's only doing. So just do it. If you get it wrong, we're gonna fix it. If you get it right, then that means when you see it again on the test, there's no problem. So what's 1? What's your top priority group on that Chiral Center?
Um.
Keep in
Okay,
mind.
so you said the OH is dashed, right? You said because it's just
Yeah. But don't worry about the direction. When you do on priority, all we care about is the atomic number.
Okay, then 2 would be the carbon on the left because it's connected to the OH.
But it's oxygen higher in atomic number than chlorine, because the carbon on the right is connected to
It's the
chlorine. Is that right?
Yes.
Because we're looking at these other 2 groups in addition to the OH group. Yeah.
Mm-hmm.
So
And
that's
then
2.
the third one would be the oxygen carbon.
There. Mm-hmm. So now, is that clockwise or counterclockwise? It's going back now. The OH is going back. So the top group is going back, and the lowest priority group is coming forward. So what do you
Okay,
think?
so it would be backward. It would be the opposite since.
Yeah.
So this would be S.
Yes, very good. It looks R, but the fact that H is wedged, we're going to turn it and make it S. Good. And then can somebody do the last one? Anybody have a question about that one? About
You're
why it's S?
turning you're turning H to the back, right?
No, I'm leaving it.
You're leaving it?
But even if I turn it to the back, it'll still be S.
Right. That's how I was trying to look at it. Like that's
Mhm.
how I was trying to count it.
You
1, 2, 3 from the back.
Yeah,
Or with the turn. Okay.
yeah. But
I could mix them.
but if we left it and didn't reorient it, then it's still gonna be S. Because what we do is we reverse what we see. If it looks like it's R, then but H is not pointed back, then we just reverse it. That's a shortcut.
Okay.
Hmm. Good question though. Go ahead. Who was that volunteering for that last one?
Brittany.
Come on with it.
So number one it'd be the OH right there, right?
Mm-hmm.
And then number two would be the carbon on the right.
Okay, good.
And then number three would be the carbon on the left.
Good. And again, the H is here.
Yes.
So what do you think?
So it's clockwise.
Hmm.
So it'll be R.
But the H is not pointed back. Right? So
The
what
H-
do you do? What do you do in that case?
So it'll be the opposite.
Yes. So
Which is
even
S.
though it looks clockwise here, the fact that H is wedged, we're gonna reverse it and call it S. We okay with that?
So that's only because H is wedged out, right?
Mm-hmm. That's the only reason. So now we know all the configurations. Is that right?
Wait,
Yeah.
I have a question.
Go ahead.
So like the second to last one we did,
Mhm.
why is the H sticking out if
Let
the
me-
OH is on a wedge?
It's actually not. The resolution is just bad. If I zoom in, you can see the lines at the bottom.
Oh, okay.
Yeah, the resolution on that is just bad. So that's why. Let me see if I can put some white.
Okay, thank you.
That's okay. How about that? Is that better?
Yes.
I just took a white pen and made it. Yeah, so H is on the wedge in this case. Uh-oh.
I have a question.
Come on.
So you reverse it if it's wedged and dashed or just wedged?
Only if it's wedged.
Okay.
If it's dashed, that's what we want, right? Because the whole idea is to get the fourth group away from you before you determine the configuration. This is just a shortcut way of doing that.
No,
See, on all the other
rest
stereo centers, H was already pointed back, right? It's pointed back here. It's pointed back on this one. On this one. You following? So we didn't have to do any type of reorientation. We can just call it like we see it. All right. So that's 128 possible stereo isomers, which is a boatload.
Dr. Russell, real quick.
Come on.
So like on the test or whatever, will the hydrogen be given to you
No.
as a wedge or a dash, or will you just have to put
No,
it in?
because if the other group is wedged or dashed, then it's understood that the hydrogen is the opposite. See how
Okay,
the OH
opposite of what
of the other group. You see how the
other group
OH
is. Okay,
right here,
yeah.
how OH is on the dash,
So the hydrogen's on a wedge.
it's
then
got to
the
be on the wedge based on the shape
Okay.
of carbon, the geometry.
Okay.
And if
if
the group was
the
on a
OH
wedge, hydrogen would have to be on the dash.
Okay, thank you.
Good question. All right, so we know all the configurations. Now here's the question. Here's another question. So what would the enantiomer look like? What is that? All right, so before we before we try to draw the enantiomer, can somebody tell me what you know automatically about the enantiomer based on what we just did with all these configurations?
It's a mirror image of it.
It's a mirror image. So what does that mean for the configurations?
That they're the opposite of the original.
Opposite.
All of them, right? Not just
Yes.
one or two. All of them will be the opposite in the enantiomer. Is that right?
Mhm.
Yes.
So if I ask you to, so I can paste this in here again. If I ask you, let me zoom in on that. I gotta leave it kind of small so I can have room to draw it. If I ask you to draw the mirror image, what would you do?
You make the wedges dashed and the dash is red. I mean wedged.
That's exactly right. So I could draw this. Let me see how many carbons this is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if I were to draw it as the, how do you want to draw it? Which way are you most comfortable with? With it facing itself or just drawing it and changing everything? Because there's, you can draw it both ways and it's still correct. You want to put the mirror right here.
That's fine.
Still don't have enough room. Shucks. Let's see. Let's shrink that down a little bit. And not right so big. So that's 13 carbons, and then I'm gonna draw it just like I see it. Right? And then what's next? Methyl, another chlorine. And then a skip, and then OH. Another skip, and then, oh, we said that other OH was -2, sorry. Right, so we could draw it like that. And that will be what? What's the relationship between these two?
So they are enantiomers.
They're enantiomers. All right. Now here's the other question. I did not try to do that. Get back up here. All right. Here's the other question. What would a diastereomer look like of the original image? Right here. This is the original. If I asked you to draw a diastereomer of that image, what would you? How would you do it?
Did you just substitute like one of the wedges for a dash
Yes.
and do a mirror image?
Yes. So you take one of those groups, one of those substituents. Come on, man. One substituent. Sorry about that. And you would change it. I got to get me one of those little gloves because my palm keeps touching the screen and screwing it up. Right. So let's take so we could just change this one. Right. We change that one on the end, and that would constitute a, I'm not going to draw the rest of them in because you can, right? That would be a diastereomer. And then we can walk the chain, walk the chain and change each one individually to give you another diastereomer. Are y'all following that? I'll put the carbonyl down here though, because I don't want you to
Oh yeah, because that's just the opposite of the original enantiomer. Right.
Yeah, this is so a diastereomer, we're looking at the original molecule, right? And then so this would be the one underneath here. Let me get this out of the way. Right, the one underneath it would be my a diastereomer of it. Now you got to remember, we said it's 128 stereoisomers possible. So you got each one of those enantiomers is going to have diastereomers, and each diastereomer is going to have a mirror image of itself, right? So that's how you arrive at all those different stereoisomers, but they're all possible. All right, any questions about that? I think this example is a good example. It's a lot going on there. All right, any questions about that? So if I gave you an example like this on the exam and asked you to draw a diastereomer, you could do that. All you're doing is switching out one of those stereo centers and reversing it. And
So
if I
question.
ask, go ahead.
So on the very end, why is the oxygen like on the bottom? Like go down a little bit.
Hold up, let me fix this right quick, and then I'll go and do that. Hold up. Okay, go ahead. Which one?
You gotta go. Okay. So like on the very end of the
Diastereomer?
yes. Why is the oxygen the same as the original pick? It was supposed to be like the opposite.
It's not. We're looking at this oxygen right here. That's the one. Oh, sorry. This is the one that I changed.
I'm talking about the one all the way on the other end. Like
the carbonyl?
No, the oxygen at the end of the branch.
Right here?
Yeah, it looks the exact same.
Yeah, because it's not a chiral center. It's a sp2 carbon.
Okay.
So I don't have to touch that because I'm only looking at the chiral centers. That's the only thing that's going to change.
Okay.
Yeah.
Gotcha.
Mm-hmm. Any other questions about that example? So we know the answer to the third question. All the chiral centers would be reversed. Right, all the chiral centers get reversed in the enantiomer. All right, let's go up. How much time we got left? Oh, we got plenty of time.
How do you make 128 though?
So you got the original image, is that right?
Mm-hmm.
You got a mirror image, the enantiomer, is that right?
Mm-hmm. Yes.
And then for the original image, you can make let me see how many. So we got 7 stereo centers. So you're gonna have at least 7 diastereomers from that.
Mm-hmm.
And then on the mirror image, you'll have another 7 diastereomers. And then each one of those diastereomers is gonna have a mirror image of itself.
Okay. Okay.
So you can definitely get to 128.
Okay.
All right. Let's do another example up top. And then we're gonna do some Fisher projections, and then we will. What's this question asking? Not that one. This one. All right. Let's do E. And let's do. I think we already did G. Let's do F. And let's do A. All right, let's start at A. And the question is, what's the configuration of each chiral center, right? So on A, you can see the chiral center depicted right here. right? It's right here. All right. So what are your 4 groups on that chiral center? That's the first question. And the second question is, what's the configuration? Right, so you can see the groups here. The ethyl group is 1, the OH is a group, the methyl is a group, and then this carbon right here is a group. So which one of those is going to be considered 1 in priority?
The oxygen.
Oxygen, good. That's 1, and then what's going to be 2 and 3?
So the methyl group is CH2, right?
It's CH3.
CH3, and the ethyl group is CH2.
The ethyl is CH2, CH3.
Okay. So then the ethyl group will be next, right?
Right, but no, I'm sorry. Let me write that properly. So the CH3 is out here. It's the CH2 that's attached. Right? So 4 is going to be here, right? Because that's just a CH3. So 2 and 3 is going to be between the ethyl and the CH2 down at the bottom.
Actually, I think the CH2 down at the bottom is
Right, because it's connected to a
oxygen.
carbonyl. Follow me?
Sorry.
That's okay. So that's going to be 2, and then the ethyl group is going to end up being 3. Let me find this thing again because it shifted over. Sorry about that. All right. So the OH is 1. The ethyl is 3, and the CH2 down below that's connected to the carbonyl is 2. So this one is kind of difficult. Well, not difficult. It's different because the 4 is not on a wedge or a dash, but we can make it. We can draw it that way. And let me show you what we can do. So we could turn this. I probably should cut it. We could turn this into a ball and stick figure and then make it to where we can rotate it. All right, I got to put this on another page because I don't want to try to squeeze it in and it's all sloppy looking. I actually should have just cut all 3 examples, but it's okay. All right, so what we're going to do is we're going to take this and we're going to make it into a ball and stick model. So we said this was 3. This was 1. That's 2. And that's 4. Are y'all following that?
Yes.
All right. So what we need to do is basically take this, rotate it so it's just a tetrahedral. So it's going to actually end up looking like this. And I know you learned that tetrahedral geometry in Chem, so just stay with me. So we're going to do we're going to put 3 up top. We're going to put 1 here. 2 here, and 4 here. So all we basically did was took this and tilted that way so that 3 is vertical. And we got the model now is easier to work with. Are y'all following that or no?
A little bit.
All right. All I did is reorient the one that I have drawn here. I just tilted it so that 3 is pointed straight vertical. If I need I should have had my model set. It'll be easier to see now. All right, so what can I do to that to get 4 away from me? because there's no shortcut on this one because the 4 is on a horizontal line. What can I do? What would you do to get 4 where 1 is?
We turn it backwards.
Right? Think about whenever you're working with like a ball and stick model like this, think about going to Publix and going to the deli, and they got those rotisseries back there, right? So you can take this and rotate it around like so. So if I do that, where is 2 gonna come?
Is 2 going to the bottom?
Yeah, if I rotate to my right, right? So if I would have grabbed 2 and pull it around this way, what will happen? 2 is going to swap places with 4, isn't it? Can you see
Yes.
that? Let me redraw it, and then hopefully you'll see it. So this will be 3. Now this is going to be 2. This will be 1. And 4 will be back there. You following that? If I just rotate it around that red axis that I drew through where 3 is. Yes, no, heck no.
No.
Do you okay, so do you see the
I mean, I
tetrahedral?
got everything until like I get what you're saying by like rotating it, but I thought why doesn't the 3 move? Like I thought it was
The
all gonna.
3, but the 3 is on the axis that we're rotating around, so we don't move it.
Oh, okay.
Like a
So
carousel.
I get it. So
Yeah.
it's just gonna stay in the same spot,
Yes, it's like a carousel.
like the base.
Mm-hmm.
Okay.
So the 2, 4, and 1 substituents, that's like the horses on the carousel, right? The 3 is the
Right.
pole that the carousel is rotating around.
Okay, now I get it.
Mm-hmm. So if I rotate around, the 2 is going to come around to where 4 is, 1 will come around to where 2 is, and then 4 will rotate to where 1 is. So now, can we tell what the configuration is? Is it clockwise or counterclockwise? Going from 1 to 2 to 3.
Counterclockwise.
It's counterclockwise. So we know that that's
S.
S. Good. All right, let me go back up here and put it in up here too. If I can find it. So that's S. All right. What about E? E is not. We don't have to apply that ball and stick model to E. We can just figure that one out. What do you think? We know the H is going to be 4, right? Is that right?
Right. And
We know fluorine is going to be 1 because it's heavier than carbon, if I'm not mistaken. Is that right? Check the periodic table, make sure I'm right about that. I want to say it's 19. Y'all could Google that by now and have me some answers. Yeah, it's 19. All right, so fluorine's 1. And then of those 2 carbons, which one is higher in priority?
Is it one to the right?
The one to the, this one, right?
Yeah.
Remember, if you're comparing those two, you see how this one is branched and that one isn't? So the one that I labeled 2 is branched. The other one is not. So we don't have to go further than that. It's just like the other examples that we did when we first started.
So as long as it's branched.
That's your point of difference,
Okay.
right? Remember, that's the rule, right? You keep going until you reach a point of difference. So when you look at those 2 carbons, the branch is the point of difference between 2 and 3. Even though 3 is connected to another carbon that's branched, which is connected to another an oxygen, the point of difference right there is that branch point.
Okay, thank you.
So what do you think? We got 1. Sorry.
It's counterclockwise, so
It's counterclockwise, right? So
um,
under normal conditions, we say that is
it's
that's S. But why do we have to reverse it and call it R?
the wedged hydrogen.
Because the H is wedged.
Yes, because the hydrogen is on a wedge. All right. So I want you to do, we already did G. I want you to do F on your own. And I also want you to do up here, J, K, and L. I want you to determine the configuration. And draw the enantiomer. All right.
Which ones are we doing again, Dr. Russell?
J, K, and L. We already did I. We did that down, but I want you to do on your own the other 3, J, K, and L. I want you to determine the configuration for each stereo center and then draw the enantiomer of each one of those.
Dr. Russell, can you scroll down a little bit? Yep, thank you.
All right. All right. Any questions about that? I'm going to put it up here too. I'm just going to abbreviate it. Y'all like abbreviations. All right. Let's look at some Fisher projections and then we'll stop. And then on Wednesday, we're going to look at that, the stereochemistry in reactions.
Oh, Dr. Russell.
Yes.
I know you sent an email out on Friday about like watching the YouTube videos, but I didn't see anything about a quiz. Is that open, or you didn't open it yet, or didn't assign it
It's
yet?
not open yet.
Okay.
Yeah. I mentioned that earlier in the class. I'll have to go and open it today.
Okay.
Yep. All right. Let's look at G and H down here. These are depictions of Fisher projections. And what a Fisher projection is, let me make sure I got room to write. Yeah, I do. I think there's a C in there. Right, it's a 2D depiction of a carbon or a chiral center. Right, and on that 2D depiction, the horizontal groups are wedged or like coming out of the page, and the vertical groups are dashed going into the page. right? So the key to these Fisher projections and determining their configurations, if H is here, then whatever the configuration is, you keep it. If H is vertical, I always like to say if it's going to heaven, let it keep going to heaven. If it's going horizontal, if it's going to hell, call it back, right? That's my little church for the day. But if H is vertical, whatever configuration you see is okay. And if it's horizontal, I'm gonna put that down here. You have to reverse it. Can you see why? If it's horizontal, is would H be wedged or dashed?
It'd be wedged.
And haven't we been doing that already? If H
Yeah.
is on a wedge, then we reverse. If it's on a dash, you just call it how you see it, right? So that's these Fisher projections. That same principle is going to apply. All right. So let's go up to here. Each one of these carbons is a chiral center. All right. So let's take the first one. Let me see how much time. We'll just do the first one and then we got to stop. But look at the first one. OH is going to be 1. Hydrogen is going to be 4. And then between these two carbons, here and here, this carbon is going to be 2. And then this carbon down here is going to be 3. Right? Because if you see on the carbon label 2, it's bonded to oxygen twice. And then on the carbon label 3, it's only bonded to oxygen once. Are y'all following that?
Yes, sir.
Right, so that top carbon is going to be 2 and the bottom carbon is going to be 3. So if we do the configuration and we count to 3, would that be clockwise or counterclockwise? If I go from 1 to 2, 1 to 2 to 3, like that.
It's counterclockwise.
It's counterclockwise, right? So that would normally be what? S, but H is horizontal, right? And so because of that, we're going to call this stereo center right here R.
Dr. Russell,
Mm-hmm.
why wouldn't the bottom group be 2?
Well, you're looking at the carbons, right?
That's right.
Yes.
And so the point of difference, this carbon is bonded to an OH. This carbon is also up top, is also bonded to an oxygen, but that carbon is bonded or bound to oxygen twice, and the one on the bottom is only bound to oxygen once.
Oh, okay.
Right.
Thank
So
you.
you don't have to go through the whole chain to find that point of difference.
Okay, I get it.
All right. So, and the fact that H is horizontal, whatever we see, we reverse it. And I think that's in the video, one of the videos I sent out on Friday. So we're going to come back and finish this example on Wednesday, and then we're going to start another topic. We're going to start the stereochemistry and reactions. All right. Any questions about anything before we stop? No, I'm over time by a minute, so I'm going to stop recording. If you haven't put your name in the chat, you can do so. I think I see 41, and we have 41. We're down at 32 now.